was just a, that was actually a trick that I learned. A guy showed me in a pub in England outside of Hyde Park. And it's all mathematical. So he did it like 4 or 5 times, and then I kind of figured out how to do it. So I won't tell you how to do it. You have to figure it out on your own. You can absolutely figure it out. I'll do it one more time here. Okay. One more time. I was like, I'm going to figure that out, doggone it. Okay. So it doesn't really matter. I'm just going to mix them up. That's not the important part. Mix up is fine. It's no big deal. You didn't slide the hand or anything. I'm just going to memorize them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay, set those aside. Lay out 3 cards. 1, 2, 3. Now I need to finish them up. 3, 4, 5, 6, 7, 8, 9, 10. 5, 6, 7, 8, 9, 10. 4, 5, 6, 7, 8, 9, 10. Yep. And then 8 plus 4 is 12. So the 12th card of the deck is going to be the 8 of clubs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, I couldn't do this online because it doesn't work online, right? I mean, it's like everyone's like, well, we can't see what you're doing. We have no idea. You know, it's not really a doable sort of thing. Okay, so let's take a look at where we are with our problem. So this is your problem. What we got here, and it was top 20%, so this is 20%. I mean, this is 0.8, right? 20% on the left, on the right means 80% on the left. So you did inverse norm of 0.8, and you got 0.84. Yeah? So this is 0.84 right there. And then you all did your x value is equal to the mean, which is 200, plus your z-score, 0.84, multiplied by your standard deviation of 20, and 216 for 8.8, so 217. Good? Yeah. All right, great. Now, we're moving on to 6.3, central limit theorem. Okay, so it's the next page, I believe? Yeah. Great. Top of the next page. In addition to knowing, okay, why am I reading this? You can read loudly. Ryan, do you have a good, strong voice?
Sure. In addition to knowing how individual data values vary about the mean for a population, statisticians are interested in knowing how the means of samples of the same size taken from the same population vary about the population mean.
Right. Perfect. So that's what we're looking at. So first, to point out, there's many different types of distributions. We've talked about 2 so far, binomial and normal. Those are the 2 we've discussed. But there's many, many, many. Like, for example, there's one where binomial, you flip a certain number of times and count how many successes you have. It's sort of the opposite. I know how many successes I want. I'm going to keep flipping until I get 8 heads. I might flip 8 times or 1,000 times. I'm just going to keep flipping until I get 8 heads. So sort of like my number of successes is fixed, my n is sort of the variable, right? That could be anything. How much time between events? So for example, how much time between white cars passing by down a highway? So white car goes by, you start counting, 1 alligator, 2 alligator, another goes by. So it's 2.4 seconds. Start counting again, 1 alligator, 2 alligator, 3 alligator, another goes by, 3.6 seconds, whatever. So time between events happening. This other one is the one we're going to talk about. Waiting for a bus that comes every 20 minutes. This is a magic bus. It comes, it starts at some point in the morning, after 6 a.m., or around 6 a.m., and when it starts varies each morning, but once it starts coming, every 20 minutes afterwards, it comes to the exact fraction of a second. Are we on board? Mm-hmm. So how long do I wait for this bus? Well, I might get lucky. I might wait 0 seconds. I get there and boom, it opens its doors right there and I hop on. Or I might get super unlucky. I get there and it just closes its doors, magic bus, it just drives off, right? No stopping for anybody. So I could wait anywhere from 0 minutes up to 20 minutes for this bus. Good? On average, if I did it over and over and over again, on average, how long will I wait for this bus? Talk to your neighbors, 15 seconds, figure it out.
Like 10 minutes. Yeah.
If you're not talking to your neighbor, I will probably call on you. Okay, Zora, how long should I wait for this bus?
10 minutes.
10 minutes. Right, because for every time that I get really lucky out here, I'm going to get really unlucky and wait over here. Right, on average, typically I might, if I get really lucky there, sort of lucky here, I might get sort of lucky there, or unlucky there. Every one of these sort of has a matching one on the other side, where you might, it might kind of, that sort of cancels each other out. You know what I'm saying? So you take all those times and add them all up. Then all the high ones, all the lucky ones will have unlucky ones a lot of times. So it kind of cancels each other out. So over the long run, if you did it millions and billions of times, you'd end up getting really close to 10. Okay. So, what's the probability that I wait between 0 and 1 minute? So here's 5, here's 1 minute. What's the probability I wait between 0 and 1 minutes? Well, I'll give you folks some hints. First of all, we know that area is the same thing as probability. Everybody with me on that part? So if I can find the area of this, I'd be okay. I'm telling you the height is 1 over 20. So the height here is 1 over 20. What's the width from 0 to 1? 1. Okay, what's the area of a rectangle?
Width times length.
Width times length. In this case, width times height. Is everyone with me? So my length times height, we'll call it that way, length times height. So what's the area of this rectangle?
1 over 20.
Yep. It's 1 times 1 over 20, which is 1 over 20. Or that would equal 0.05, right, or 5%. What's the total area underneath the curve? 1 or 100%. Good. All right, so what's probably wait between 5 to 10 minutes? See if you folks can figure that one out with your neighbors. Probably I wait between 5 and 10 minutes. Of all the distributions, this will actually be the very easiest one of all. Finding probabilities, you just multiply length times height. Good to go.
I just went over inhaled once and I was fine. She was just saying.
You know how you like choke?
I was like, I can't cough like crazy in this room. I'm gonna freak out.
Oh, yeah.
Wait, so this one's, I don't think this is on your sheet. So what's probably that wait between 5 and 10 minutes? It is. Really? 20? Oh, 5 to 10 minutes. Yeah. 5 to 10 minutes?
25%. 125.
What's my height?
120.
So is everyone drawing this in on your sheet? Find your height. I've given you the height. Find your length. Find your area.
Yeah, or no, it's 1 point actually. 5 over 20 equals
What's the height of the rectangle?
1 over 20.
What's the distance from 5 to 10?
5.
So the area is
5.
length times width. 5 times 1 over 20. And you should get 5 over 20, which is 1/4, or 0.25. Okay? Now, here it is pretty. Now the question comes, on the exam, it's going to be a little bit harder. You're going to have to figure out what some things of your own. You're going to figure out the height on your own. So first of all, what's the area under the, what is the total area under the rectangle? What does it have to equal? 1 or 100%, right? So how do you find the height? Well, how do you find, so if the area is equal to 1, remember area is equal to your length times your height. What's my length here? 20. From 0 to 20 is 20. So 1 equals my 20, my length, times my height. What's my height have to be?
On the screen.
What multiplied by 20 gives me, what multiplied 20 gives me 1.
1 over 20.
1 over 20. All right, the reciprocal. The reciprocal of 20 is 1 over 20. So that means my height must be 1 over 20. Can I see your sheet, please? All right, so you folks have a problem below that, which is a friend says they'll come over in 15 to 30 minutes. So the very next problem down in your sheet. Find the height of this rectangle. Find the height of this rectangle. How high is it? And what's the probability they'll arrive in 20 to 25 minutes? So let's figure out the height of the rectangle. Everybody take 15 seconds to neighbors, find the height of the rectangle. What's the height of this rectangle?
We have 1, 2, 3 problems left, so.
I'm dragging on. I just don't want to use.
How do you like that?
Do you not like it? Have you seen it?
No, what kind of trigger is that?
Okay, yeah, I mean, if you can't do like, kind of like, it's just kind of twisted, but.
Yeah, sorry, I agree. I think just your favorite show in terms
I was like, you know,
this girl I was talking to, the girl I was talking to, she finished it, she was like, that was like really good. I haven't finished it.
Me either. I'm like 4.
Oh, I was on the 3rd one right now.
Yeah, I'm gonna go this
Wait, no,
far.
I'm on the. Hopefully, no. The one I just watched Gil did the whole face.
Oh, that's awesome.
I don't like all the things.
Okay, let's do the second part before it all goes away. So my distance from 15 to 30 is what?
15.
15. So that means my height has to be what? 1 over 15. Has to be the reciprocal because you multiply them, you have to get 1. So what's the probability they'll arrive in 20 to 25 minutes? Everybody take a couple minutes and sort that one out. Okay, so what did folks get for this 20 to 25 minutes? So let's see, 20 is maybe here, 25 is maybe there. Okay, so a couple things I want you folks to get used to. This is my big L. My big L is 15. This part here is just my little tiny L, my small length within the giant length. Do you see what I'm saying?
Yeah.
What's my small length?
5.
5. What's my height?
1 over 15.
115. So my area will be my length times my height, my small length times my height. 1/3 or 0.333. Good? Okay.
Wait, Miss Young?
Yes.
For these, how do you want us to do the
Hey, I can't hear quite. What?
the decimal? Like,
If you want to do 3 or 4 is fine. Right? So maybe if you want to do 4, just so you keep it consistent with the other ones, that's absolutely okay. Normal is the only one where I need 4. Everywhere else, 3 is fine. But we can do 4, 3 or 4 is okay. So we'll do 4. Is that better?
The other connector's down.
Yeah, I knew that was going to happen. Okay. All right. So question. Can everybody see this one way over here? All right. So here's the thing. My average wait time is 10 minutes, right? But if I take a sample of 30 people, 30 people's wait times, how long did you wait? How long did you wait? How long did you wait? 30 people, and I average them, I might get an average of 11.24 or 9.43. Is that making sense for folks?
Yeah.
Good? Okay, so it's not necessarily going to be perfectly accurate. Now, here, imagine I do that 12 times. I take a sample of 30 people, I average them. I take another sample of 30 people, I average them. I take another sample of another 30 people, I average them. Over and over again, another sample of 30 people, I average them. And I do that 12 times. So each one of these averages represents 30 people and their average. Everybody with me?
Mm-hmm.
So these are all averages. These numbers all here, up here, are all averages of 30 people. Good? Central limit theorem says that these means, these averages, will be centered around 10. We expect them to be about 10, right? So will be normally distributed. So it means they're centered around 10. Most of them are around 10. And as you get further and further away from 10, fewer and fewer. So most of your averages are going to be right around 10. And as you get further away from 10, there'll be fewer and fewer averages that will be, that will be those numbers. So that's what central limit theorem says. It says, even if my data didn't start off as being normally distributed, it started off being uniform. If I take an average of 30 of them, the averages, the means, will be normally distributed. So me and my grad student friends, when we took statistics, we talked about it, we kind of tried to wrap our heads around it, and we came up with the idea of mean of means. So we're talking about means, we're talking about means of those means. So we kind of know that what we're dealing with is not x values, they're means. And I think that was helpful for us at least. So maybe think of it that way. All right, so how does this affect us? Well, first of all, the mean of the means. If I take all these means over the millions of these means, sample 30, their means, another sample 30, their means, another sample 30, their means, thousands of times, all of those means, all those averages of 30, will have an average of the regular average, 10, right? That's what we expect. It shall be right around 10. So, filling the blank, the first blank you're going to fill in, down under central limit theorem. Well, the first one you fill in is central limit theorem. But the next one you're going to fill in is mu x bar equals mu. Okay, everyone take a deep breath. Clear your mind. Let it go. So we're dealing with central limit theorem. It's a tricky concept, right? It's not hard, but for the next 3 minutes, I really need you folks super focused on this, and then it'll be a piece of cake. So again, we're dealing with mean and means. We have all these averages, and these averages are normally distributed. Their average, the average of the averages, the mean of the means, is just mu. That's what you expect. But the standard deviation of these averages, sigma x bar, is different. It's the ordinary, the regular, the old sigma divided by square root of n, which is already written in for you because it's super important. Good. So in other words, it's the standard deviation of all these means will be the old standard deviation, but smaller, divided by the square root of n. That's going to make it tinier. The larger your n, the bigger your sample size, the smaller that standard deviation will be. Yeah?
Sorry, this is going kind of backwards, but what does it mean that the sample means are normally distributed?
What does it mean that the sample means are normally distributed? So that was this one here. Right, I take a sample of 30 and I average them. I take another sample of 30. I take another sample of 30. I take all the samples of 30 and I average each of them. Those are each one of those numbers up there represents a sample of 30 and their average. So the first sample of 30 had an average of 11.24. The next one had an average of 10.41. The next one had an average of 10.86. So each one of these represents, each of those numbers represents the average of 30. Does that make sense? So the central limit theorem says that these averages, these means, will be normally distributed. So in other words, they'll be centered around 10 minutes, and there'll be more of them will be right around then, and as you get further away from 10, there'll be fewer and fewer of them.
Okay.
That's what that means.
Thank you.
Yeah, you're welcome. All right, so now we're taking a look at this standard deviation. Why is the standard deviation smaller? Well, this is why. Oops. No, sorry, my bad. This is why. Who remembers Steph Curry in 2016? That was the year he took the ball in with 3 seconds to go from halfway, took a dribble, and then put the ball up, swish right in, right? He had 2 54-point games that season. Everyone remember that? Okay, good. So for Steph Curry, that season, say his average was 30 points. That seems reasonable. With a standard deviation of about 10, because we know he definitely had some 50-point games. So a 50-point game would be right on the borderline of unusual, right? It's possible, wouldn't happen often, but it could happen sometimes, right? So here, this makes sense. A mean of 30, standard deviation of 10, because 10, 20, 2 standard deviations, right? We get to 50. So 50 points would be borderline unusual, but reasonable. However, if I took a sample of 25 of his games, random sample, would that random sample ever have an average of 50? No, that's crazy, right? That's just not going to happen. Because for every game that I grab that he gets a 50-point game, there might be another game I grab where he only scored 10 points, right? So they'll balance each other out. When you take a sample of 25, you'll get some high games, but you'll also get some low games. Randomly, they'll balance each other out. So you're going to get something a lot closer. Your distribution is going to be a lot. This blue line represents the sample, the average of 25 games. If I took every possible sample of 25 games, it would look like that. So you'll notice that it's a lot more narrow, smaller standard deviation, right? Because it really is going to be a lot closer. It's not going to be. You're not going to get an average of 50. Because, like I said, the balances are out. You're going to get stuff a lot closer to the mean. And if you look at that, that makes sense. Because if you think of it sort of realistically, here's my 30. I go standard deviation this way, another standard deviation that way. 50, another standard deviation one that way, one that way. That's sort of in my range of usual. So that gives me a standard deviation of 10. What does central limit theorem say? It says my sigma x bar. Give me just a couple minutes here. All right, so if we look at the standard deviation of 10, what does central limit theorem says? It says, well, my sigma x bar should be my regular standard deviation divided by square root of n. What's my standard deviation? And what's my sample size, n? How many people did I pick?
25.
25 games? That's my n. What's the square root of 25?
5.
5. 10 divided by 5, 2.
Okay.
So then my sigma x bar will be 2. Make sense?
Yeah.
So that's going to kind of be right more like 1, 2, kind of right from here to here. Most of my day is going to fall right in there. Good? Does everyone sort of fall on this okay? All right, so there's a couple conditions you folks need to write down. Here they are. first one is the original variable is not normal. A sample size of 30 or more is needed. Fill in your blanks. If the original data is normally distributed, then any sample size n, any sample size will work. You don't need the n. Okay, good. Yes, there is. All right, everybody do problem number 29, or sorry, problem number 7? Seven. Do problem number 7 on your lap. Take 60 seconds, do it. Do it, do it. The formulas you need for it are directly above. It's like they're like a third of the page up above that. They're right there. Veronica? What was it right there? Find it. Right here, right here. I thought it was you in there. Okay, so the mean UX bar is just mu. 86, that was easy, right? Next one is sigma x bar. That's going to be sigma over square root of n. So why is it called x bar? Because it's the x bar is my sample mean, the standard deviation of the sample mean. Okay, and that's going to be, what's my sigma? 8. What's my n? 24. 8 over square root of 24. So find the square root of 24 first, and then write it down, and then take 8 and divide by that, or however. And you folks got what? 1.633. Okay, terrific. We're not done yet. Hang on. I still have a couple minutes. Why is it useful? One way, there's lots of ways, but one of them is if we take a sample, and it's 30 or more, we can find the probability that that sample is unusual or not. We can find the probability of getting a sample like that. So we can see if it's what we expect to get or if it's unusual. And if it's unusual, we can write a paper. So it's kind of the nice thing about it. And the thing about it is, it doesn't matter if it's normally distributed. If we take a sample of 30 or more, then the mean is normally distributed. Okay, so here are some examples. I have a couple to show you very quickly. First thing, A.C. Nielsen reported children between the ages of 2 and 5 watch an average of 25 hours. Average of 25 hours, that's my mu. Standard deviation is 3 hours. That is my sigma. If 20 children are selected, between the ages of 2 and 5, what does 2 and 5 mean? That's just your ages. That has nothing to do with your problem. You don't need it. It's just telling you what children are. So we're picking 20 children. That's my n. Thank you. Find the probability. Aha. So one big question I get from people is, Ms. Young, how do I know if it is a central limit theorem problem or it's a regular chapter 6 problem like 6.2 problem? The probability that the mean, not the probability that the one person, that I pick a child. Right, before with our problem, the probability that a chocolate bar, one chocolate bar is between 200 and 220 calories. This is a mean, right? A mean will be between those. That's a whole different story. The mean of these children, of this sample. So that's the first way. The probability of a mean. Not that we have a mean. You always have a mean. but the probability of a mean. Does that make sense? The second one you figure out is it has an n. There is a sample size. We have a sample size of 20. Not a sample size of 1. It's not just one chocolate bar, it's a sample of 20 children. So those are the two ways that you know it's a central limit theorem. Will be greater than 26.3 hours. That's my x, or my x bar. So first I find my sigma. I need 2 more minutes. I got 2 more minutes with folks. That's going to be sigma over square root of n, 3 over square root of 20. You find that. And then I find my z-score. Right? So take my x bar, subtract the mean, divide by the standard deviation, I get 1.94. So then when I draw my picture, here's my picture, here's my notch, 1.94. I want larger than, it's going to be over here. So then it'll do normal CDF. Of 1.94, comma, any large number. This is infinity out here. Pick 600, and you'll get 0.0262. So basically it's the same exact thing we've been doing before. The only difference is we have one added difference. Instead of using sigma here to find the z-score, use sigma x bar. 3 over square root of 20. That's the only difference. The only difference between this one and the previous ones is, again, instead of using sigma, we're using sigma x bar. I want one more thing I want to point out to you folks really quickly. All right, average time spent by construction workers working on weekends. So if we have one individual, my sigma is 0.8 for one guy. My z-score is 0.09. If I take a sample of 40 people, my sigma is 0.8 divided by square root of 40. That changes my z-score. My sigma is 0.113, so now my z-score is going to be 0.55 instead of 0.09. So my probability will be 54% instead of 71%. It's totally different, right? All because my standard deviation is different. You got to use sigma x bar instead of sigma. Okay, so that's central limit theorem. We'll go over more of it tomorrow, but that's the basics. All right, we'll see you folks tomorrow. Have a good one.